So in this lecture, I will keep talking about one-dimensional flows, and main point here will be analysis of logistic equation. So let me remind what we did last time. We had a one-dimensional flow represented by differential equation, Bernoulli's differential equation. Then we can plot function f of x, assume it's something like this. Then what we can say, points of intersection with x-axis equilibrium points. This is x1, this is x2, this is x3. And then if, so this equilibrium points, in between equilibrium points, sign of function f of x is not changed. So in order to change it, should cross x-axis. So if we here, for example, f of x is positive, here f of x is negative, here f of x is positive, and here f of x is negative. And when it's negative, then x is decreasing over time. When it's positive, x is increasing over time. Here it's decreasing. X dot is negative, x dot is positive. Therefore, what we found that we have, for example, this x2 is stable fixed point. And in addition, we can find what is domain of attraction of x2. This is domain of attraction. Domain of attraction of x2. So all this line, all of this represents a range of possible values of x, and it shows also illustrates what is dynamics of solutions, what kind of orbits we can expect here, or what kind of solutions. And this is called, generally it's called phase portrait. So in case of one-dimensional map, it's called phase line. For 1D flow, sorry. Okay, and so this is pretty much a summary of what we discussed before. Now I will consider two examples. Example one. So it is linear map. X dot equals to ax plus b, linear flow. Linear flow, and let's say a is non-zero. At one hand, we can be solved analytically. You all can do it. So what we have is dx over dt ax plus b, separation of variables, dx over ax plus b equals to dt. Then we can integrate it. So this will be 1 over a logarithm of x plus b over a equals to, say, t plus constant. And then I'm skipping parts. X plus b over a will be equal to a times e to the power of a small t. So a is constant, arbitrary constant. And at the end, we can find constant. So if we supplied here with initial condition x at t equal to 0 equals to x naught, these initial conditions, then we can find a, and a will be equal to x naught plus b over a equals to a times e to the power of a times 0. and therefore A is x naught plus b over A, and therefore x will be equal to x naught plus b over A times e to the power of at minus b over A. So this is solution, analytical solution. On the other hand, so and from here we can see, okay, I will put it here, x naught equals to, sorry, x function of t equals to x naught plus b over A times e to the power of at minus b over A. We can plot it. So solution, this is time, this is x as a function of time. Let's say this is minus b over A. If x naught equals to minus b over A, it will stay minus b over A for all times. This is because if x naught equals to minus b over A, this will be 0, and x of t will be equal to minus b over A forever. If x naught plus b over A is positive somewhere here, then this will be increasing up to infinity. And if it's less than minus b over A, it will get down to minus infinity. So this is what we see from, and from here we can see that this is x equal to minus b over A equilibrium. And now, so this is what I plotted. This I plotted when A is positive. So it's therefore unstable if A positive, and stable if A is negative. If it's negative, then what we will have looks like this. This is minus b over A. This is time, this is x, and now they all converge. So it is stable in this case. We can also apply our method, which we consider it now for this. So it's called qualitative method, qualitative analysis. So again, x dot equals to ax plus b. So we find equilibrium f of x equals to ax plus b equals to 0. And from here we find equilibrium x equals to minus b over a. And stability. So derivative of f over x equals to a. And therefore, if a positive x equal to minus b over a is unstable, and if a negative, then x equal to minus b over a is stable. So what we did, we found what is going on in this system without finding exact solution. So what we have minus b over a. It is the equilibrium point or stationary solution. And then if a is positive, we have this kind of solutions, a positive. And if a is negative, this will be convergence. Okay, so this was warming up, and now we will consider logistic equation. So this is example logistic equation. So logistic equation is quadratic. X dot equals to we will keep the same notations as before for parameter Rx times 1 minus x. So what we have our function which defines our flow is Rx times 1 minus x. If we plot it, let's say here R positive, say x is, well, x could be any. So this is our x, f of x. So this is our plot of x. So it is f of x 0. Roots of this is x1, which is 0, and x2, which is 1. So we have two fixed points, 0 and 1. And from here at 0, derivative of x equals to 0 is positive. We can see it from here. It is positive here, and it is negative here. Derivative of x equals to 1 is negative. So this is unstable, and this is stable. Therefore, we can put it like this. This is time, this is x. So this is x1 equal to 0. This is x2 equal to 1. So what we know, this is stationary solution. This is stationary solution. So we consider solutions for positive time only, for example. And then here will be convergence to like something like this. And from here also. And here will be divergence. So again, x1 equal to 0, unstable, and x2 equal to 1 is stable. So this is stable. This is unstable. So it's again, so we didn't solve, we didn't find exact solution for logistic equation. Nevertheless, we know how solution depends on initial conditions. So if x naught is positive, then f of x, then orbit or solution tends to 1. If x naught is negative, then x of t tends to minus infinity. And if x naught equals to 0, x of t equals to 0. So this is all conclusions we can make using just applying methods. That's finding, just by finding equilibria and analyzing their stability. All of this can be done also. So for this logistic map, it's relatively easy because we can find analytical solution for this exact solution. Logistic equation. So again, so dx over dt is rx1 minus x. So we can separate variables. It will be dx over x times 1 minus x equals to rdt. Then integral of dx over x times 1 minus x will be equal to integral of 1 over x minus 1 over x minus 1 dx. This equals to logarithm of x minus logarithm of x minus 1. This will be equal to logarithm of x over x minus 1, say by absolute value. And this should be equal to integral of r dt, which is rt plus constant. So what we got? We got this logarithm equals to this rt plus constant. And if we take exponent from both sides, we will get x over x minus 1. This will be equal to a times e to the power of rt, where a is constant, which can be found from initial conditions. So that if, again, so if initial value of x is x naught, then x naught divided by x naught minus 1 will be equal to a times a capital times e to the power of r times 0, where it is equal to a. So this is a. And finally, x of t will be equal to, after simplification, I will just give final expression. 1 over 1 minus x naught minus 1 over x naught times e to the power of minus rt. So this is, I skipped a couple of steps, but you can find some out. You can show this. And now what we see here, if we plot it. So if x naught equals to 1, then x of t equals to 1 always. So this is fine. This is 1. If x naught equals to 0, then we can't use this formula because we have here division on 0, but we can look back in here. If x naught is 0, then the x over dt will be 0 and will stay 0 always. So this is another stationary solution. I will put maybe right. This is stationary solution, this is stationary solution. And now, since e to the power minus rt tends to 0, when t tends to infinity, x of t will tend to 1 as t tends to infinity. It's one conclusion. And this is in line with our analysis which we did before, based on equilibrium and zero stability. On the other hand, if we look here, we will find out that x of t is increasing. So here, let's put it like here. So here, it is increasing. It is fine. It is decreasing. It is fine. But here, what we had before, here it should decrease on one hand. On the other hand, it should tend to 1. Tend to 1. And this is a question. So we can see that it will be decreasing if we look at here. So what we see is so when t is 0, then this term is when, let's consider if x naught is negative, then denominator at t equal to 0 is 1 minus x naught minus 1 over x naught, which is 1 minus 1 plus 1 over x naught. Since x naught is negative, it is negative. On the other hand, when t tends to infinity, second term disappears. Denominator 1 minus x naught minus 1 over x naught times e to the power of minus rt is tending to 1. So it's negative, tends to 1, therefore at some point it should get at 0, and we can find out. We can at certain time 1 minus x naught minus 1 over x naught e to the power of minus rt equals to 0 at certain time. Yeah, so we can find this time and assume it is this time t capital. And when denominator is 0, x of t will be infinite, so it will tend to infinity. And this is what happens in reality. So our solution tends to minus infinity here, and then here it comes from plus infinity, and again converges to 1. So there is kind of complication with solution of logistic map, which is not seen by our qualitative analysis. In qualitative analysis, we just seen this. Here it tends to minus infinity, here it tends to 1, and here, so here we have tendency to minus infinity, here we tendency to 1, and here we have tendency to 1. But in fact, this tendency to minus infinity stops at certain time t, and then we get this continuation of this orbit in here from up and also tends to 1. Okay.